to this evening's session. We're having a look at differentiation this evening, okay? Looking at how you can access the different ways to demonstrate and calculate using differentiation. There'll also be a little bit of integration in as well, because obviously they're a matching pair for calculus, okay? Let's launch into the session this evening. Just a little bit about myself. My name's Simon. I'm Casio's principal trainer. I've been working with them for about 10 years now, 5 years full-time with them, making resources and training teachers how to get the best out of the handset so they become more effective learning tools. Okay. Before being full-time, I was in fact a teacher, and I used to use these handsets in almost every single lesson when teaching A-level maths and further maths. Okay, that would give students a good experience using the handsets so they can see how useful they were, and hopefully you will see that during this session. Who are Casio Education? What do we do? Essentially, we're here to help teachers. Calculators we think are quite useful in the classroom as a teaching and learning tool. So we do offer induction sessions, training how to use the handset. For both the graphical and the scientific, there's emulators available. We do student support with training webinars and revision webinars. There are loan sets available, obviously deep dives, which you're attending this evening. And very soon we're launching an on-demand certified CPD course where you can have a go at training yourself how to use the handset. Like I said, tonight we're looking at differentiation. And what does that mean? Well, to start off, if you wouldn't mind, if you could just have a look at the poll on the screens so you can give us a clue as to what handsets you are using, whether you use the CG50 or not. It just gives us a little bit of feedback so we can tailor our training a little bit better for you. So thanks very much. It looks like you generally recommend, okay, a few mandate, but generally recommend, which is fine. I do understand that there are problems with a mandate in the handset, but recommending it, hopefully you understand how useful it is. Okay, so thanks very much for that. So just to have a little bit of an insight into why we do these sessions. We believe it's for learning, not just for using in an exam. Obviously, students can do their own investigations. They can switch between different formats, say numerical and graphical, enables the understanding to be improved. They can pursue their own ideas, you know, just independent learning, which is always useful. And they get to check whether they're doing the right thing or not. Okay, so using the handsets is always useful for your students. When dealing with differentiation, though, what are the possible problem areas that they may come across? Interpreting the derivative, you know, numerical value or even the algebraic version. What does it mean? What does it represent? Stationary points can also be an issue, including points of inflection, for example. What about tangents and normals? That's always an interesting part of A-level exam questions, finding the equations of them and doing something with that. And also remembering the relationship between functions. So, for example, a function and its derivative, and maybe even its second derivative. Okay, so what we're going to do is we're going to look at differentiation in terms of calculus in mechanics. Okay, we're going to have a look at the position of a particle given by, in this case, a cubic. Okay, so we've got S, the position, and T, time. I should say, if you do have any questions, please enter them in Q&A in the background, and I will try to answer them at the end of the session. Okay, so we have our cubic. This gives you an opportunity to discuss perhaps with your students about the shape of the function and its importance. You know, what could it possibly mean? We can have a go at plotting. On the emulator, I've actually reset the emulator. If you haven't done that before, it doesn't matter. You may not get the same uh, images on your emulator. But I'm going to enter graph mode with the shortcut 5. So I'm going to have a go at demonstrating how to do this. You don't have to follow along at home, but you can if you want. So entering 6x squared, subtract x cubed, and subtract 5. Okay, so we've entered our function. However, if we have a go at drawing it, you'll get something that looks a little bit like this, and that's not a particularly useful curve. Okay, that's because we're using the initial scale settings, and unfortunately our function doesn't quite fit in there. Okay, so what we can do is have a go at changing the scale settings. I can quickly use view window there. And if I just change the vertical scale, I think it's something like -50 to 50. I exit and draw, and I get something that looks a little bit better. Okay, so we've got a complete cubic curve there with the two stationary points and all the roots shown. However, because this is in context, we're going to have a go at investigating it between 0 and 7, so 0 and 7 seconds. Now that makes sense, given that negative time is not particularly relevant to our questions. So we do have to pay attention to the importance of the domain that's given. So what we can do next is change the view window so we get an even better looking curve. So we've got the initial settings. I would then go to view window again, and we want to optimize our view as best as possible so that we can still see all the roots and the stationary points, and everything that is relevant. So what we're going to do is have a go at changing our horizontal scale to go from -1. The reason I'm including a negative is because that displays the y-axis. It just makes life a little bit easier. I can go all the way up to 7. I can keep the scale as 1, and if I change the vertical scale to go from -40 to 30, that should be quite nice, and let's have a scale of 10. Okay, if I exit and redraw, I now get a very nice looking curve with all the relevant parts displayed. Okay, so you don't have to stick to those settings, but it does help if you do. Most of the time I do leave quite a large gap at the bottom because that's where you get the displayed values. So what we can do here is, because we're going to do a little bit of changing, is I'm actually going to store this as a view memory. So shift and view window, can you see view memory, F4? That allows you to store and recall settings quite easily. So I can store, and there's 6 slots available. I'm just going to store them in slot number 1. Okay, and that allows me to come back to these settings quite quickly without having to manually enter the values if we do change anything later on. Okay, so what we can do now is ask various questions. Because this is in context, I'm taking liberties and in that respect, and I'm using it to demonstrate a point. Okay, obviously this is relevant to other questions when it's not being used in calculus, but we're talking about particles' average velocity during the first 3 seconds. Okay, well, what you can do is you can in fact trace the points and enter a value. So what happens at x equals 0, or in this case, s equals 0. I can execute to fix that point, and then I can add another value, what happens when t equals 3. And you can see that I have gone from a position of -5 all the way up to 22. To calculate the average velocity, what you'll do is a straightforward calculation. The change in position over the change in time. Okay, so that gives me an average velocity of 9 meters per second. Okay, there is a sort of correlation here. What you could do is actually do an integration. Later on, we will be entering our function for the velocity, which is the derivative of our position function. Okay, and you can integrate that between 0 and 3. And to get the average, you divide it by 3. So there you get the integral of 27 divided by 3 gives you the average of 9. So you can see there is a nice correlation there between using calculus and just tracing the points on the position function. Okay. Using calculus in run matrix, though, generally, okay, there is a couple of ways you can approach this. I'm going to go to run matrix. So you can do calculus both in graph mode and run matrix. So they're a nice partnership going on there. So you can make sure that you are understanding things completely. There's two methods, like I say. First of all, you've got math available as your on-screen choice. If you choose that, you can see that you've got first and second derivatives available, but choosing the further menu with F6 gives you access to the integral template as well. The second method, which I actually prefer, is using option and calc. If you've ever attended one of our induction sessions, you've probably seen this before because that's how you access solve n. Here you've got first and second derivatives as well as the integration template all on the same screen. Just makes life a little bit easier. Okay, so now that we know how to access our calculus templates, first and second derivatives and integration, we could have a go at using them during this session. But first, let's approach velocity at a given point. Where is the particle and how fast is it moving after 3 seconds? Well, the way that you would do that, find its position, is you could substitute 3 into the equation for it. So that's quite easy to do. And then you would substitute 3 for the cubic and then subtract 5. And you can see that's actually, it's easy to do, however, slightly clunky, shall we say. Or alternatively, because we have sketched the function, we can use graph notation. Okay, so this is y1 of 3, so equivalent to the function f of x, just doing f of 3. To access your function, you can use the vars key and graph. These then list your functions. Y is not a letter, that's actually a function. So that is y1 of 3. Okay, so that gives me the position of it. How fast is it moving though? Well, to do that, you would differentiate your position function. I can exit, and if I just delete everything, oops, there you go, give you a clear screen. I can then use option and calc and my first derivative template. I can enter my function. And again, you can see that it's a little bit slow, and then differentiate at a point, and it gives me the value of 9, so I can work out what its velocity is. But why not use the graph notation? Because that avoids any input errors. Also, it does allow you to automatically recalculate if you change the value of the function y1. So again, I can just delete those and use the vars key and graph to enter my function y1. And if I recalculate, I get the value 9 again. So that's just two ways of approaching differentiating a function. Quite nice if you have graphed it. But what if we continue with a velocity at a given point questions? When is the velocity of a particle 0? So the way that you could interpret this is graphically, or alternatively, you're saying when is the derivative of my position function equal to 0? You can solve that quite nicely using solve n. Okay. So option, calc, and solve n. So this demonstrates nicely that within solve n, it does more than just solve equations. You can straightforward polynomials, for example. You can also use differentiation within it and integration. So let's use our first derivative template, and I'm going to stick with using the graph notation. Okay. I am differentiating at the general point x, and I need to equate this equal to 0. Although actually, if it is equal to 0, you don't need to enter it. Okay, but for the sake of completeness, I'm just demonstrating that. And then when you execute, you get the two values of 0 and 4, excuse me, for when my differential or my velocity function is equal to 0. So initially, obviously, it is stationary, and then also stationary at t equals 4. If you want to find out its position, then what you can do is, what is y1 of when t equals 0? So that's -5, which you saw earlier on the graph. You can also find out when the, oops, sorry, there you go, when it is stationary again at the second value, 27. Okay. So that is your position, s equals 27. There is something else that you can do just to demonstrate how effective the handset can be. Well, these values, 0 and 4, are quite nice to enter and replicate. But what if they were decimals? Okay. Or even surds or something? Difficult to say what's y1 of my value. You could actually, if you wanted to, extract the values from the list, and you can do that with the list label, which labels 1. So let's go list answer. Now, I've got two values, 0 and 4. I want to use the second one, so I use some square brackets to tell the handset I'm using the second value, and it'll give me 27 again. So that's quite a nice way that you can extract values from a solve n. Okay. So that's when we've got our velocity equals 0. What if we were interested in sketching or evaluating our velocity and acceleration functions? So this makes a nice link to the rate of change function. So in this case, it is position, velocity, and acceleration, but it could just be a function and its rate of change function. We can enter the first derivative of the position equation. So let's go to graph. Okay. We've got a choice. We can actually enter what we think the first derivative is. Okay. And that might be quite useful. However, there is potential for error at this point. You may not have differentiated correctly, especially if it's a more interesting function. So what we can do is, instead of actually entering what we think the derivative is, we can actually use the differentiation template. You could, of course, enter what you think the derivative and then compare it to the actual derivative, and then you would get some coincident graphs which would prove that you are correct. But let's enter the derivative template. We use this with option again and calc. It has changed position though, although the functions available are the same. First derivative, okay. We need to either enter the function as it is, but that will limit it to only ever being the derivative of that function. If we use graph notation, that allows us to change the function y1, and our derivative will automatically change. So that's quite handy. We do need to differentiate at the general point x. Otherwise, it would be a constant. And we can also then enter our second derivative as well. So option calc, second derivative, and we can do the second derivative of y1 again. So this is all referring back to the function y1. So if we change y1, first and second derivatives will change automatically. Okay. So that's quite useful. We know we can draw the actual derivatives. But perhaps we may be interested in evaluating some of these functions to start with. So if we go to table, shortcut 7, you can see that quite nicely these functions have been carried over from graph to table, so I don't need to enter them again. We can have a go at evaluating some of these functions. Okay, so for example, we have been asked what happens at t equals 3 before. We need to set the table to the relevant values of x that we want values for. So let's choose set. Default is 1 to 5, so let's change that from 0 to 7. We could go up in other values, but just going up in integers is fine for the time being. Okay. If we exit and then choose table, we get our table of values. So you can see that the blue values are the precision function, red ones are velocity, green ones are the acceleration in this case. So we've got first and second derivatives being shown. Quite nicely, you can see that the velocity was 0 at t equals 0. We can scroll down and see that the velocity is also 0 at t equals 4. And it gives us the associated values of s equals 27 that we calculated earlier as well. So a nice way of approaching the function. You could also investigate what the value of the second derivative equaling 0 means at t equals 2. So that could prompt nice discussion of second derivatives equaling 0. What does that mean? You can interpret the motion of the particle using these values. You can also, if you wanted to, as you would expect within table mode, just enter a particular value and re-evaluate. It should be pointed out, however, that when you have values in the table, they are truncated. Okay, so if you want a value, it's always worth highlighting that and investigating the full decimal. Okay, so please bear that in mind that the table values, as in stats mode as well, they are always truncated. If you wanted to, you could even have a little bit of a sketch. Okay, here you can see that we've got a continuous sketch going from point to point. So it gives us a rough idea of the shapes of the functions. And if you really wanted to, you could have a go at tracing a point as well. It will only trace to the calculated points and you can't enter a value, but it does give you a good idea. For example, t equals 3, we've got a position of 22. Okay. So another way of demonstrating the evaluated points. But what is most effective on the handset is you can toggle whether the derivative is calculated or not. This does aid when you have got some graphs. It automatically gives you dy dx, for example, and it makes a nice link if you've got more than one function between the function and its derivative. So what we can do is shift and setup. And if you scroll down to the bottom of the screen, you can see you can toggle derivative on or off. I'm going to turn it on. Okay. And then I can exit. If we go back to table mode, just a second, just to demonstrate that the derivative values are found automatically, what I'm going to do is deselect the first and second derivatives. Okay, this is just to demonstrate how useful turning on the derivative is. That if you deselect those with F1, the calculator will no longer calculate those values. And you can see that now I've got my position function and the derivative of it is automatically calculated. Okay, so that's quite handy. If I had left the first derivative on there, I would have also got the first derivative. So let's just demonstrate that. So these two columns should have the same values, which makes sense. And I'll get the derivative of the first derivative, so my second derivative is also calculated. Okay, so turning the derivative on is actually quite useful. Okay, if I just deselect that one and table again, now when I graph, so I've got a continuous graph going on there, and I trace, you can see that I get the dy dx values calculated. I don't get the dy dx function drawn because I would need to actually enter the first derivative function, see that, but I am getting the value of dy dx at a point shown. Okay, so as you can see, dy dx equals 9, which we saw earlier. We can make some links between functions, which is quite useful. Let's have a go at sketching just a single function. So let's go to menu. We're just going to draw the position function. So let's deselect those. So you can see the equal sign no longer highlighted, so it's deselected. And then when I sketch, I just get the single graph. Okay. I could draw both of them if I wanted to. So I'm interested in the relationship between the position and the velocity. I could then select that and draw it. Or if I wanted all three functions, let's select my second derivative so that I can make some conclusions about the relationship between all three functions at the same time. We can analyze points using trace, which is quite useful. So let's do shift trace. It automatically toggles to Y1 at the center of my screen. So I've got 322. You can scroll along, but you can see you may not necessarily hit the value of X in this case that you want. So you can just enter a value if you need. So we've got 322. Notice, because I've turned the derivative on, I now get the value of dy dx equals 9, which I can confirm if I just toggle between the functions. You can see that my velocity function at x equals 3 has a y value of 9. So a very nice confirmation of the relationship between the position function in this case and the velocity function. Okay. I could also enter a value of 2 on my position function, and that tells me that y equals 11. So that is its position, but my dy dx is 12. So again, oops, sorry, I can scroll up to my velocity function, and this time it tells me that the gradient of my velocity function is 0. Which you may have come to notice because the green acceleration function has a root at x equals 2. Okay, and potentially that should lead to a discussion about, is there a point of inflection going on my position function? Okay, so a nice way to demonstrate the relationship between the functions. You could then, because this is mechanics, say what is actually happening to my particle. It was speeding up and then it wasn't. Okay, it's still moving in a positive direction though, so no negative values, but at the point of inflection, what we have is a maximum value of our velocity. Okay, so a nice way of making that connection. Next thing we can have a look at is we can analyze functions, obviously. We can investigate the points of interest, so maximum points and roots, for example. We can use gsolve for that, as you would expect. So let's do gsolve of my position function. Let's find, in this case, the maximum. Now, because there's more than one function being sketched, you need to choose which one to analyze. It always starts with y1, so that's flashing. That's the one I want, so I select it with execute. And you can see that the maximum occurs at x equals 4, and it has a position of 27, which we saw using the table values earlier. We also have dy dx given, so that proves or demonstrates that the gradient at that point is 0. It's a maximum. Okay. As we saw before, you could trace a point from your position function to the velocity function, and it would have the root at x equals 4. So again, confirming the relationship. So just to demonstrate that, we could then do the root of a function. Let's scroll down to the red velocity function. Initially, when x equals 0, we had a root, so that confirms that the particle is stationary. And then if we toggle to the right, you can see that we get x equals 4, velocity is 0. And that the second derivative is negative 12. Okay, so again, in the context of demonstrating whether you have a maximum of a function, demonstrating that dy dx equals 0 is a requirement, but to demonstrate its maximum, you've also got the second derivative being negative. Okay, so you can make kind of links between other functions outside of mechanics. Okay. So that's interpreting the results. You could, of course, say when is my second function, which is the derivative of my position function, when is that equal to 0? So you could approach it numerically. So that would be solve n. And if I use vars and graph, I'm just saying when is y2 equal to 0. Notice I'm not equating it to 0 because you don't have to. And when you solve that, it confirms that it is at 0 and 4, which we've just demonstrated graphically. So you've got a choice there, numerical or graphical. It does help your students give them that option. Okay. One of the things that is important when dealing with differentiation is that we are interested in tangents and normals. Okay. So I'm going to demonstrate how to deal with those now. Let's have a go at sketching a single function. Ooh, that was definitely the wrong one. There you go. I think I am just going to deal with the velocity function. Yep, the velocity function. Okay. Nope, got to, there you go. Let's deselect that one. So there's my velocity function. Just because this will give the best tangent and normal of the three functions we've got. We can sketch the tangent quite easily. That's shift and sketch, where we've got the choice of drawing tangents, normals, and also inverses. If we choose tangent, we get a tangent at the center of the screen, so that happens to be x equals 3. But let's, you can then use a scroll pad to move it if you want. But let's just enter a particular value. Let's go for 4. So what we have here is we've got a tangent at x equals 4, or t equals 4 for time. Okay, and we've got a dy dx displayed, which is the gradient of the tangent, which we saw earlier from our tables. Okay, but what we can do with the tangent is slightly more than this. We can actually define the equation of it. So here we have a gradient of negative 12. If you press execute, the calculator then works out what the equation of the tangent is. Negative 12x add 48. Okay, so that's quite useful if you have a question that requires you to get the equation of a tangent. But also you could sketch the normal if you wanted to. So we can shift, sketch, and normal. Again, places it at the center of the screen. If I just enter a value of 4 again, so let's have the normal at the same point. What we've got there is our normal, but notice that it does still quote dy dx, not the negative reciprocal. Okay. However, that doesn't look particularly like we've got a gradient of a negative 12th. We can define our normal equation by pressing execute again. Okay. But one of the things that is worth pointing out is that the tangent and the normal should be perpendicular. And on our graph at the moment, it doesn't look like that. Okay, and that is because we don't have any square scales. Okay, they are uneven. So what we need to do is change the view window. So let's stick to -1 to 7. But if I change the vertical scale to go like that, I can now use the square option from the view window to either choose a Y base or an X base. If I choose the Y base, you can see that automatically changes the horizontal scale. And now when I draw, I should be able to, you can see that the scales are square. I should be able to sketch both the tangent at 4 and the normal at 4. Okay. What I do need to do is fix the tangent though, so let's fix that at 4. There you go, and shift and do the normal at 4. And you can see that makes much more sense as they are now perpendicular. Okay, and you can see that the equation is, what is it? Negative reciprocal of -12. Yeah. Only displayed as a decimal though. So that could lead to problems as students may not be able to recognize if that is a fraction or not. And we'll cover that in a second or so. But just to finish off analyzing your different functions, displacement or distance traveled. Now, this is normally, shall we say, referred to for integration. We're just going to have a look at the velocity function between 2 and 5. This is where it comes in handy that we stored the mem settings, because you can see that they have changed. So Shift, View Window, and vmem allows us to recall from position 1. And if we exit and draw, we get back to our original graph. Okay. If we're only interested between 2 and 5, we could integrate under the curve with mixed integral limits. So that's a G-solve, a further menu, and integral. There are in fact 4 different integrals that you can perform. We're going to choose mixed as opposed to limits, just to demonstrate something else. You enter your lower bound first and then your upper bound of 5. And it integrates for you. And this is quite nice because if you used mixed, for example, it gives you the integral as well as the area. And as we know, there's a difference between displacement and distance traveled when you are integrating under the velocity curve. Okay, but it may not be immediately clear which one is which. Okay, so that's why what we could do is actually compare with the position function. So let's bring that back. Let's exit and sketch our position function again. What I'm going to do here is just integrate between limits now, though. If I was to use mixed integration, what would happen is I'd get the area between curves. Okay, so if I just integrate between limits, you can see I only get that integral value now as opposed to the area value of 23. Okay, now if we're looking for displacement or distance travel between 2 and 5, we could actually trace some points. So let's trace what happens at 2. I can pin the point by pressing execute, which is quite useful. I can also say, well, what happens at that maximum of my position? Well, we know that happens at 4. And what happens at 5, which is my upper bound? Okay. And if I close trace, you can see that I go from the position of 11 to 27 to 20. So the difference between 11 start point and 20 the finish one. Okay, that would be my displacement. However, the distance traveled is 11 to 27 and then 27 to 20. So that will give me my 23. Okay. So that's a nice way of demonstrating the link between the area under the velocity function and the position. Okay, the distance traveled or the displacement. Just to make it clear that you can differentiate and draw tangents to Cartesian functions or e to the x, something like that. Or you can also do it to parametrics and polars. Okay, so we're just going to have a go at sketching some of these. I'm going to sketch a circle. So let's exit. I'm going to delete my first and second derivatives. And then I'm going to change the type of function to parametric. Okay. Now it looks like the center of this circle is at 3, 1, and it's got a radius of 2. So let's do 3 plus, what is it, 2 cos t, and then do 1 plus 2 sine t. Okay. And I'm not getting the circle as expected because remember these are not square axes, so I need to go Shift View Window and use the initial settings. These are square, so that gives me a nice looking circle. You can sketch a tangent if you want, so Shift and Sketch Tangent. Notice it will place it at t equals 0 initially. I'm going to put this at pi over 4, so let's just enter pi divided by 4. You can see quite nicely it does give you the values of dx, dt, dy, dt, and also dy, dx. And you can also define the Cartesian equation of the tangent with execute again. So that assists with your calculations. Okay, that looks suspiciously like negative x plus 2 pi. Okay. You can also sketch a normal if you like. So let's sketch the normal. Again, placing it at t equals 0. Let's do pi over 4 again. Again, you get dx dt, dy dt, but remember it is dy and dx and not the negative reciprocal. Okay, and you can find the equation of the normal as well. X subtract 2. Okay, so quite nicely you can do that with parametrics to help your students out, for example. You can also do it with polars. So just quickly exiting that and deleting these functions. Let's change the type to polar. This is was it 2 sine 3 theta to give me the petals? And there is my drawing. I can shift and sketch the tangent. Again, this places it at r equals 0. Sorry, not r equals theta equals 0. If I then change it to, I think this is pi divided by 6. There you go. That is my tangent at pi divided by 6, and I can get the Cartesian equation of it as well. Okay. So you can do it with polar and parametric, Cartesians and polynomials and other functions. Okay. So just to demonstrate, because we have sufficient time, what if you have problems that involve differentiation? Well, here's one. This is f of x equals trig function, and we're talking about the normal at pi over 2. And we're told it crosses at 3 points between 0 and 2 pi. The question is, find the area bound by the normal and the curve. So essentially, this is an integration question, but before you get to integration, you need to determine the equation of the normal. Okay? So you can sketch the function and then sketch the normal. Okay, it doesn't quite look perpendicular, but that's not really a problem. But you can confirm that it does cross the function 3 times in the given region. Obviously, it's got another point of intersection just off screen. So what do we do? Well, we can find the points of intersection. And we can find the equation of the normal. There it is, negative pi plus what looks suspiciously, sorry, negative x plus what? Plus pi. Okay, it looks like it could be pi, but that may need verifying. So in order to do that, let's have a go at checking the normal. You can use algebra, which means that you differentiate your function and substitute pi over 2, which then gives you the value of 1, which makes sense if you've got negative x plus pi. You could differentiate at a point. Okay, so because we have graphed it, we can use graph notation. So that's confirming that pi over 2, we've got a gradient of 1. Then we need to find the equation of the normal. So we can use the y subtract y1 equals m multiplied by x subtract x1. Because we've got a point and a gradient, that gives us the equation y equals negative x plus pi. Okay, so that pops out quite nicely. But we can also use solve n to try and solve y equals mx plus c. Okay, so notice that we are using negative 1 over the answer because that is the negative reciprocal of the gradient of the tangent at x equals 2. We are attempting to solve for c. Now, normally this wouldn't work because there's a y, an x, and a c, 3 unknowns in my equation. However, if you enter it carefully using the letter y and the variable x, the values of y and x are brought forward from the graph at the point pi over 2. So that's why we are able to calculate the value of c, our constant, as pi. So that's quite nice, especially if it's not such a nice value. Okay, so using solve n in this context can confirm what the equation of the normal is. Then you can find your intersections quite easily by sketching and just finding intersect. It is confirming that actually it occurs at the root. Okay, you could then find the end or right-hand side point of intersection, and it's got a fairly nasty value of x. Doesn't pop out as anything particularly nice. So you are integrating, in this case, between, what is it, pi over 2 and 5.8. Okay. Now, unfortunately, that may be awkward to do manually. So therefore, we can do this numerically. what we can do is find these particular values. So y1, so notice this is not the letter y now, it is the function y. So this is my trig function. When does it equal negative x plus pi, which is the equation of the normal we found? We are solving between 0 and 2 pi, and it gives me the 3 points of intersection. Now, this is important because we are interested in our last point of intersection. That allows us to store that as a value by extracting it, as we demonstrated earlier, from our solution set and storing it as a value that then allows us to integrate, do a mixed integration between our functions between negative pi over 2, sorry, not negative pi over 2 and a. Okay, so you don't have to try and re-enter this particular value because it's an unpleasant decimal. So that's quite a nice technique for using when you are integrating or even just doing something with one of the values that pops out from solve n. But we can finish this session off just to demonstrate. Okay, here is a typical exam question. This is from MEI. And what we have here is we've got x cubed and a normal, sorry, not normal, a tangent at a point, and they are asking to integrate essentially between the two functions, between some limits that you need to work out. Okay. Initially, it says, what is the area of the triangle? So that means that you may need to establish what the equation of the tangent is. So we can sketch the two functions, place the tangent at x equals 1, and determine what the equation of it is. Okay. This is quite a nice equation, so we can see where it is going to cross the x-axis is a nice value, but it may not necessarily be a nice value. So what you can do then is plot the tangent. Just as we have seen, you can confirm what the equation is and then plot it and work out what the y-intercept is. And in this case, you can actually do an integral of your tangent equation between 0 and the root of it, which you have determined, and the y-intercept, which looks suspiciously like it is negative 2/3. And you can confirm that if you wanted to by doing that numerically. If you finish the question off, obviously, you could then solve where your equation of the tangent has a root. You can actually use the extracted value in an integral as well. And you could integrate, as we have seen, between the limits of 0 and, in this case, 2/3. So if that was an unpleasant value, you could use it as an integral. This gives you negative 2/3. Again, it's below the x-axis, hence the negative value. Second part of this question is, what is the value between the function and, x cubed and the tangent between 0 and x equals 1? The way that you could approach that is doing it numerically. So upper function subtract lower function between 0 and 1 gives you the area, or approach it graphically. So you can't do either of those until you have got the equation of the tangent. So you can see quite useful within context.